The great scientist Michael Faraday. He was among the pioneers doing study on the electrolysis or the effect of current on solutions. He did it on both aqueous solutions as well as melts, and in his experiments he derived two laws known as Faraday's laws of electrolysis. First law is amount of chemical reaction which occurs at any electrode during electrolysis by the current is proportional to the electricity passed through the electrolyte. So mean current, which is I, passed for t time. So total charge that we have passed through it is I into t. That is the amount of charge we have passed through a solution. Charge on a single electron is 1.6 10 to minus 19 coulomb. So charge on 1 mole of electron will be single electron charge multiply 1 mole, which is 6.02 10 to 23. In total we are getting a 96,487 coulomb per mole charge, which is known as a Faraday's constant. So for n moles, we simply multiply this Faraday's constant with n, which is total charge on n moles of electrons. For reducing magnesium ions to magnesium metal, we require 2 moles of electron. To reduce 1 mole of aluminium 3 positive into aluminium, we require 3 mole of electron. So depending upon the valency of a particular element, we require number of moles of electrons. So let's see here. To deposit 1 mole of magnesium to positive, we require 2 moles of electron, which is 96,487, roughly 96,500 coulomb charge into 2. So let's see, if you're passing a current for 10 minutes, which is nothing but 600 seconds, we require total charge divided by time, 321 ampere current roughly we have to pass through a solution for 10 minutes to deposit 1 mole of magnesium over it. Second law of Faraday's is the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. What is a chemical equivalent weight? Chemical equivalent weight is the atomic mass of a particular metal divided by the number of electrons required to reduce the cation, or simply the valency of the cation, particular element. Here is equivalent mass, atomic mass divided by valency. So quantity of electricity required will be current into time. Quantity of electricity is nothing but a charge here. So 1 unit of a Faraday charge, which is nothing but 96,500 coulomb roughly, will liberate 1 equivalent mass of an element, which is atomic weight divided by valency, that is equivalent mass. I into T, the coulomb charge, will liberate mass into grams. Quantity of electricity is current over charge into equivalent mass divided by 96,500 coulomb of charge. That much current will be required. So if we pass I current for T time, it will give us a particular amount of charge that will liberate mass in grams is equal to total charge equivalent mass divided by 96,500, which is a 1 mole of electrons charges. For example, for silver, we having a equivalent mass of silver is 108, which is a atomic mass, divided by 1, which is a valency of unisilver. So 96,500 coulomb of charge will liberate 108 gram of silver. For copper 2 positive, it will be atomic weight of copper divided by 2, which is a valency. So 96,500, which is a 1 mole of electrons charge, it will liberate 1 equivalent mass of copper, which is 63.5 divided by 2, or nothing but 31.75. Now, factors that affect products of electrolysis. First is chemical properties of material being electrolyzed, type of electrodes being used, different oxidizing and reducing species present, first we are having a sodium chloride here, melt, we pass a DC current through it. Now, chemical properties of materials, what we will get? Sodium will deposit on that cathode, chlorine will be liberated on anodic side. Because sodium get reduced here on cathode, chlorine will get oxidized on anode, is a positive terminal, and if it loses electron on anode and gains electron from cathode. Now, aqueous solution of sodium chloride, if we electrolyze it, we are having extra protons and hydroxyl ions. At cathode, what happens? Sodium ions as well as protons are available on cathode. Here we see the cell potential of sodium minus 2.71. For proton it's 0. Thus, relative propensity we will see which will be get reduced. The probably high chances will for proton will get reduced on here. And at anode, in a competitive environment, we have a chloride as well as hydroxyl ions. Chloride having 1.36 and liberation of oxygen or hydroxyl ion, oxidation requires 1.23 volt. And here we see protons get reduced selectively because they are having a lower, while sodium ions, they are not that good oxidizing agent, while sodium is a very good reducing agent. That is the reason it will not able to get reduced here that easily. Now here chloride preferentially get oxidized, liberating a chlorine gas on the anode, compared to hydroxylines. That's the reason sodium and hydroxyline are accumulated in a solution. The solution turns out to be alkaline or sodium hydroxide solution, and we are getting liberation of gases from cathode and anode respectively. Next is concentration of species affect the electrochemical reaction as it affects the standard electrode potentials. Electrolysis of aqueous H2SO4 gives us different products at different concentrations. At dilute concentrations of H2SO4, we are getting H2O, oxygen get oxidized to this oxide get oxidized to oxygen, elemental form, and 4 electrons will lose. At high concentrations, sulfate ion, what happens here? Here sulfur's our oxidation number is +6. In this one, sulfur's oxidation number will be -2, 16, 14. So sulfur oxidation number will go down. So here is the oxidation of sulfur. So we see two different reactions are happening in aqueous solutions at different concentrations. So concentration is also affecting the products of electrolysis. Now type of electrodes we use, whether it's an inert electrode, platinum electrode, or any other electrode, is used for sink of electrons. If the electrodes are reactive, it participates in electrode reactions, and products of electrolysis may be different for reactive and inert electrodes. Here we are having liberation of hydrogen and chlorine for inert electrodes, platinum electrodes. What if use some electrodes that are not inert? It may participate in a chemical reaction with electrodes. What we'll see, corrosion of electrodes will start and some other products will also be formed. That's what we see. Corrosion products will go into a solution. In competitive reduction or oxidation of species with the standard electrode potential closer to hydrogen, that is equal to 0, with a positive standard electrode potential which is close to 0, they will reduce first. Species with a negative standard electrode potential close to 0, they will get oxidized first. It's a competitive environment. Who will lose this electron first? This will happen if our standard electrode potential is only dominating factor. In many cases, we have complex scenarios where the other species influences and the standard electrode potential is not only the dominating factor present in solution.